Good afternoon, everyone. Today we're going to use implicit differentiation to differentiate this equation. Okay, so on the left-hand side, we're going to start here with the product rule. So we'll do the derivative of this first bit. That'll be just 3 times y cubed. And then by the product rule, we'll do the first bit times the derivative of that second part. So 3x plus 2 times. Now remember, we're differentiating y cubed here with respect to x. And so that'll mean the power rule, the same we always do. So y cubed will differentiate into 3y squared. But then since we're differentiating a term in y with respect to x, we have to include that dy dx part, okay? That's the new bit in this differentiating technique, okay? So then we can move on to that second term, the 2x squared y squared. So we'll again use product rule. So we'll have 2 times the derivative of x squared, namely 2x times y squared, right? And applying the product rule means we also differentiate that second part. So plus 2 times x squared times the derivative of y squared. And again, we are now differentiating something in y with respect to x, and so we get as a derivative 2y times dy dx. Okay, anytime we're differentiating in y with respect to x, we have to include that dy dx term, okay? And all of this is equal to the derivative of the right-hand side. Don't forget to differentiate both sides, right? The derivative of x, of course, is just 1, okay? Now, what we're aiming for here is to get dy dx completely isolated, kind of the same way that we learned to isolate a variable when we learned the first steps in algebra years ago. We're trying to simplify this entire left-hand side that allows us to isolate that dy dx. Okay, so we can have it by itself at the end and have an expression for it. Okay, so let's try to clean up whatever we can clean up here. We'll have 3y cubed plus. What I'm going to do here is write this this term here as 3y squared bracket 3x plus 2 times dy dx. Okay, you'll see why in just a moment. Plus 2 times 2x times y squared, that is 4xy squared, plus 2xy times 2y, that's 4x squared y, dy dx. I'll put a bracket just to be very thorough there. And all of that is equal to the right-hand side of 1. Now, what I'll do here is everything that has a dy dx component, I'll leave on the left-hand side, isolating dy dx later on. And everything that doesn't have a dy dx, let's move that to the other side, okay? So I'll even write it out. Subtract 3y cubed, that has the dy dx part. Subtract 4xy squared, that has a dy dx component, and so we'll do the same thing on both sides. Minus 3y cubed and minus 4x y squared. That goes away, that goes away. So now we have 3y squared, 3x plus 2, dy dx, plus 4xy, x squared y, dy dx, being equal to 1 minus 3y cubed minus 4x squared y, okay? And again, the entire, the goal of this problem is to find an expression for dy dx, right? And so we want to isolate that component of the left-hand side. So let's factor it out of both terms. Since we have it common to both terms, we can factor it as such. And so we can write it as dy dx times this plus that. And so that'll mean 3y squared times 3x plus 2 plus 4x squared y, still equal to the right-hand side of 1 minus 3y cubed, whoopsies, minus 4xy squared, okay? And we're almost done. To get dy dx by itself on the left-hand side, we're going to divide through by everything inside these big brackets on both sides, obviously. And so we go ahead and divide both sides by all of this, right? Yeah, that's not gonna simplify any. I'll just leave it as 3y squared bracket 3x plus 2 plus 4x squared y. Again, 3y squared bracket 3x plus 2 plus 4x squared y, right? And so these two simplify down, and we finish with an expression for dy dx of 1 minus 3y cubed minus 4xy squared all over 3y squared bracket 3x plus 2 plus 4x squared y. And we're done. Okay, so there is an expression for our derivative dy dx. Now remember, this is the slope of a line that is tangent to this curve. If we were to plot, this on a graph, this is the slope of any line that is tangent to the curve at any particular point on the curve. And if we wanted to look at any particular point on the curve, we would simply need their respective x and y coordinates. We would plug in those x and y coordinates into this expression, and that would give us the slope, right? The instantaneous rate of change of the tangent line to the curve at that specific point, okay? So, hope this helps. Thanks for watching.